lecture number 4. Continuing with comparison of molecular sequences, now with pairwise alignments and score matrix. To compare sequences, if we have two sequences, how can we compare them? We can place them side by side. How? We have different ways to look at the sequences. Perform alignments of two sequences, and they can be uninformative or they can show some information. If we place them side by side only, we can check if the nucleotides in this case do correspond, are equal or identical, or have no corresponding. If they don't have corresponding and other places have, we could introduce gaps in order to improve the alignment. But how can we measure? How can we get which is the best alignment? So we must give some scores. We must give some value to the substitutions or to the non-corresponding nucleotides, or give some penalties or punctuation to the existence of gaps. And most of the times when we have multiple possible alignments. So those several multiple alignments, we have to measure and have a score in order to identify the best alignment according to its best score. The higher, the better, but it's not equal to the correct alignment. So how can we do pairwise alignments? We can only have a graphical view of the alignment. So we will place the sequence in the horizontal and simultaneously in vertical, starting from the 0. So in the, for example, the x-axis and the y-axis. And you can identify what is in common. And you can see that in this sequence, that is a sequence fictitious, representing not only nucleotide sequence but a protein sequence it could be, but this one is abracadabra cadabra. And this sentence you can see that is aligned with itself. So you have a diagonal central line complete from the top to the bottom that denounces that the sequence is exactly the same. But behind saying that it is actually the same, we can check there are some repeats. And the repeats is, for example, parallel lines that show up. And these parallel lines to the central diagonal, they represent repeats. For example, abra, you have it here, you have it here, and you have it here. It denounces that it is in here, abra, once again in here, abra, and then in here once again. So these repeats are repeated in the sequence. So the pattern is the appearance of diagonal, parallel lines. Also, you can have palindromes, so sequences that show in a cross. It is in this side and to the other. So you have ACA that can be read from the beginning to the end or from the end to the beginning. So you have a cross represented because it is a palindrome. Palindromes are sequences that can be read from one side to the other the same way. The same happens with ADA here. Okay? And these are graphical representations that we can apprehend the existence of patterns, repeats, palindromes. But it is also used to check if a full sequence is a palindrome, like Maxi stay away at 6 a.m. If we align it with itself, we can see that if we want to see the corresponding higher than 10 window size, it only shows the full length of the sequence, and you can have two lines cross. So this is a palindrome, but you really need to highlight the window that you want to show. If you have a window of 1, you can have a lot of noise. All the corresponding and identical nucleotides or protein amino acids will be signed out. So you have a lot of blur and a lot of noise, and that backgrounds your graph. If you change the window, you can have the less detail, but you can highlight the structure. For example, this palindrome. Another use of these dot plot alignments, graphical alignments of two sequences, is to identify the number of exons. But then you have to use the full sequence of a gene aligned with the full sequence of the transcript. So when you have this gene with 2,718 base pairs aligned with 1,551 base pairs, then you have highlighted only the regions that are identical or exactly the same nucleotides exist in the cDNA and in the gene. So those are the exons. We count 1, 2, 3, 4, 5, 6 exons. The gene is bigger. It has a beginning that doesn't exist in the cDNA, and there's an end that doesn't exist in the cDNA. So dot plots are possible to perform between two sequences, but the result is a graphical view that you cannot ensure the size and where the exons start and ends. There are examples also with proteins. If we align TBP1 with TBP2 proteins, you can get the results of the corresponding identical sequences, and then you have a sequence longer than the other. TBP1 is longer. It has 1,922 nucleotides. So these are cDNA instead of protein. But then you have a big square that represents the repeat of a codon. And you have the TBP2 that is smaller. So there's a region that doesn't exist, but we don't know where is the place. Or we can see which are the nucleotides or the amino acids, if it were proteins, that exist in here that made this appearance of repeat. These two transcripts were aligned using these conditions, a zoom 1 to 7 and a sliding window of 59. in order to have less noise on the background. But we can see which nucleotides are repeated here. So this kind of graphical alignment called dot plot that we can use a software developed for that called Dotlet that is available in several platforms like Swiss Institute of Bioinformatics, for example. It's not enough to know which are the nucleotides or amino acids repeated, the place where the alignment is identical and where it is not, where are the gaps. So there are pairwise alignments, different, that may be used. And this is not graphical, it's the pure sequence alignment. And for that we can use two types of pairwise alignments, global and local. To know which alignment is the best, whether it is local or global, we need to weight the alignment. So some measures of similarity were developed. Hamming distance, Levenshtein distance. Hamming distance only counts the number of different nucleotides aligned or amino acids. The Levenshtein distance also counts the differences even if they are gaps. But these kind of measures are still very poor, although Levenshtein already counts for the types of mutations, insertion, deletions, and substitutions. So we must use to weight the substitutions based on a scoring scheme. For example, if we change between purines, adenine to guanine, it is between the same group, so the transition is quite more often and weights 1 in this matrix. If we have a change between a purine to a pyrimidine, like for example an A to a T, you have a weight of 5. So it has a heavier weight and punctuation in this scoring scheme. There are several scoring schemes, mainly based on the properties of the amino acids. If you have, or in the properties of the nucleotides. In this case, about the amino acids, you have different groups. You have the small amino acids and the tiny ones. And you can have also the amino acids that are positively charged. So if you change a lysine that is represented by K to an arginine that belong to the same group, you have a substitution between amino acids from the same group. But if you change these positively charged to a different group that belongs to threonine, that are dipolar with charge but differently charged, and also a small amino acid, you have a non-conservative substitution, so it must have a different punctuation. It's less probable to exist. So different substitution matrices were designed. Margaret Dayoff was one of the persons that developed the first point accepted mutations in 1978, and he observed mutations from 71 families of closely related proteins. At that time, there were few proteins studied, although based on this, she could prepare a substitution matrix and weight the substitution of one amino acid to the other, and all the matrix is 20 to 20 amino acids. And The scores of the amino acid, the scores and the index of this percent or point accepted mutation matrix is mainly based on the differences, the mutations that show up. So it's inversely corresponding to identity. So low identity between proteins have a higher index of PAM matrix. Higher identity corresponds to lower level or lower index of PAM matrix. Later, after PAM matrix being developed, and you have several different according to the proteins analyzed and the level of identity, and you have different ways to present them. There was a growing number of proteins available. So at a certain time in 1992, Henikov and Anikov developed a new kind of substitution matrix based on blocks substitution matrix. And those substitutions are analyzed by the point of view of conserved patterns among families of protein less related. So it is the index of the blossom matrix is corresponding exactly to the level of identity. So a blossom 80 corresponds to 80% identity between the sequences. So the less related sequences have to be analyzed with a blossom with low index. Blossom 62 is the matrix more often used, and it may be represented in half matrix or full matrix, and it's used to quantify the substitutions. And you can see that there are differences between, so the objective according to what we need, we will use PAM or blossom. PAM is more often used to phylogeny, blossom is more used to identify patterns. But there's not only substitutions, sometimes you have also deletions. So the deletions are represented by a gap. And how can we weight gaps? There are several ways to weight the gap. At DNA alignment, it may be only match-mismatch and give a weight of +1 or 0 or -1. And the defined of gap opening penalty, it may be defined according to the level of identity and the type of sequences in analysis. Gap opening penalty, it often is 10 times higher than the gap extension penalty. So what is a gap opening penalty? Gap opening penalty may be defined as a positive number, but in fact it's a penalty, so it will be subtracted to the sum of the substitutions weights. So the score is the result of the sum of all the punctuation in a substitution matrix and subtracted the gap opening and gap extension penalty. The gap opening penalty, if we decrease the gap opening penalty and gap extension penalty, we get higher score of the alignment. So if we want to compare several pairwise alignments, we must use the same parameters values. The best score or the higher score usually corresponds to the optimal alignment, but it is not exactly the biological correct. So it may be incorrect, although it has to be analyzed. At this time, there are many dynamic program or heuristic methods to improve the best alignment, but because we can analyze and perform pairwise alignments with sequences very, very long. there were defined two types of alignments: the global, based on the algorithm of Needleman and Wunsch, and the local alignment based on the algorithm of Smith-Waterman. There are many other algorithms to perform these types of alignments. The global alignment, it matches the sequence from the beginning until the end and shows the results of all full alignment. Local alignment will perform the alignment and will only show the sequence that highly align. The basis to develop this algorithm, for example, in Smith-Waterman, is derived from Needleman-Wunsch. And Needleman-Wunsch defines the algorithm as having different ways to get one sequence to the other and then choose the way that has the best results. And the best score may be according to different points of view. For example, if you travel, you may have different parameters to analyze. If it is less distance or more quickly or less cost, Needleman-Wunsch asks for the way that has and results in the best alignment with the best score. So you have an algorithm that you can calculate the best way to get from one sequence to the other. Smith-Waterman algorithm derives from the previous one, but it's less complicated because you don't align the sequence from the beginning until the end. You only show the perfect alignment between the higher values in the matrix obtained applying the Smith-Waterman alignment. And this is one of the results of an alignment. Pairwise alignments best score don't mean that you have the correct alignment, but represents to you, and if you ask for more than one pairwise alignment, you get ordered by score the several pairwise alignments. But pairwise is limited. You only analyze two sequences. So a pair of sequences whisper, but you can get more interesting results if you can perform multiple alignments. And this will be the subject that we will focus on lecture number 5. Thanks for your attention. Meet you soon at practical or other theoretical class. Bye now.